Good morning to all of you once again. Today, I'm going to start with module 5. In that, two topics I'm going to cover, if possible, in today's class. One of them is digital to analog conversion. The other one is analog to digital conversion. Okay. So let me move on to the class notes. This is module 5. Module 5 consists of two chapters, uh, namely op-amp circuits. We are going to discuss a variety of op-amp circuits even in module 5. You might remember, in module 4 we have covered even few op-amp applications. We've introduced op-amp and we have covered a couple of applications in module 4. The extension of module 4 is in module 5. Even in module 5, we are going to cover few important op-amp circuits, namely analog to digital converters, digital to analog converters, etc. Along with this, we have one more chapter on 555 timer and its applications. We will see how to build various applications using 555 timer. Okay, now in today's class we will be covering analog to digital and digital to analog converters from the textbook Ramakant Gaikwad. It's 8.11. Okay, let me introduce to you what is analog to digital and digital to analog converters. Basically, we can represent analog to digital and digital to analog conversion with this block diagram. In this block diagram, we can see there are three blocks mainly. The first block would be analog to digital converter, which accepts analog signal as an input. Analog signal means it's a time varying signal, maybe sinusoidal or cosine signal, which is varying with reference to time, is applied as an input to analog to digital converter circuit. Here this block represents circuit that converts analog input, a time varying input, to a digital output, which is basically ones and zeros. Here we have a digital system. Basically it is a microcomputer which accepts digital data, data in the form of ones and zeros, process that data and gives the output in the form of once again in the digital form, ones and zeros. The processed data is very difficult to interpret, because ones and zeros, you all know that when the information is represented in ones and zeros, we can't interpret what it represents. So that's interpretation becomes very difficult when the data is in digital form. Only from a processing perspective, we convert analog data to digital form, and again, once the digital data is processed, it becomes very difficult for us to interpret. Therefore, we need to convert digital data to analog form. Okay, once again, to convert digital data to analog form, we need another type of converters here, basically digital to analog converters. The circuit here converts, takes input data as in the form of digital, and gives us analog output. This analog output is easier to interpret because it's in favor of the human. So therefore, the analog data is more convenient than the digital data for interpretation. Okay, so this block diagram represents various blocks involved in conversion of analog data to digital, then process the digital data, then convert back digital data to analog format. Okay, the same is discussed in the following notes. Figure 1 shows the block diagram of a analog to digital and digital to analog conversion. The digital system basically it employs ADC and analog to digital converter and digital to analog converter. And the digital system is basically a microcomputer. In today's world, we can use ordinary computer or desktop computer or maybe supercomputer to process the digital data. So that represents our digital system in the block diagram. The reason for using digital microcomputer or computer for digital data processing is as follows, because the data in the digital format is very efficiently we can process it, and it's more reliable and more economic also. So for these three reasons, we use computer in place of a digital system to process the digital data. Analog data processing is very difficult because it has too many values, so it's not efficient. Analog data processing, and it's not reliable, and also it's not viable also, analog data processing. And therefore we need to convert analog data to digital and process in digital form. Since we humans interpret in analog form, we need to convert back digital data to analog format. The reason would be this for using computer as a digital system to process the digital data. Yes, let us see in the block diagram. First block is digital to analog converters. How we can convert digital data to analog format. Once we understand this, we will also understand how to convert analog data to digital format. So digital to analog converters can be represented with the help of this block diagram. There is some circuit inside this. This circuit is going to accept digital data as input, converts that into analog format, and provides as analog as an output. Here you can assume this input data is a binary data, which is in the form of zeros and ones. This circuit here, an op-amp based circuit. Right now we are going to discuss op-amp based circuit, which converts zeros and ones to a voltage format. Maybe say 0001 may represent some voltage here. So that's the block diagram representation of digital to analog conversion. Looking at definition, we have definition of digital to analog conversion as follows. A digital to analog converter converts digital data in the form of zeros and ones to analog output. Analog output means it's some voltage that's equivalent to the digital input. The analog digital to analog converter employed here uses op-amp. We can use op-amp either in inverting mode or non-inverting mode, but not in open loop mode. So here we will stick to any one of this mode, not both. So let's assume that we are going to use op-amp in inverting mode rather than non-inverting mode. Okay, we will see that in the following session. Okay. So what are the various types of digital to analog converters? Broadly, we can classify digital to analog converters into two types. One of them is binary weighted resistors type digital to analog converter. As the name suggests that the resistors are in the form of binary weighted. Okay, you know that binary weighted means it's 8, 4, 2, 1. 8 means it's 2 to the power of 3. Since I'm taking 4-bit digital representation, therefore the binary data can be called as 8421 also. Since it's a 4-bit data, I'm accepting as an input. So here each resistors are in the form of are connected in the form of binary weights. So therefore this converter is called as binary weighted resistor type digital to analog converter. Another converter which is more efficient than the binary weighted resistor type digital to analog converter is R-2R resistor type digital to analog converter. Binary weighted resistor type of DTU converter has few drawbacks that can be easily overcome in R-2R resistor type digital to analog conversion. Okay, so now we will start with binary weighted resistor type digital to analog conversion. We'll try to understand the circuit details, analysis, working, so all those things related to these two converters, and let's see them. So digital to analog converter with binary weighted resistors, and let's take up straight away the circuit. The circuit is as shown here. Just minimize the, yeah, you can see full circuit here now. So this is the circuit details of binary weighted type digital to analog conversion. As I already mentioned that here we use op-amp, that's the basic element in this conversion process. Op-amp is used in inverting mode since we apply input signals to the inverting mode, and the non-inverting terminal is grounded. That's voltage at non-inverting terminal we call as V1, that's stator weight is grounded. And op-amp has got implicit power supplies such as plus VCC equals plus 15 volts, minus VCC is as minus 15 volts. These voltages can be varied according to the manufacturer specifications. This can go up to plus 22 volts, plus or minus 5 volts to plus or minus 22 volts. In this example, we have taken here as plus 15 volts for normal circuit operation. And the op-amp used is not the mu-A741, it is mu-A351. It is more efficient than the mu-A741. So 351 is the op-amp widely used because it overcomes few drawbacks of mu-A741. Op-amp is used in ideal mode, therefore op-amp doesn't draw any current since we assume that input impedance is very high, so therefore current going to the op-amp is 0. And also we need to understand the virtual ground concept here. Since V1 is physically grounded, the voltage at V2 will be similar to the voltage at applied at non-inverting terminal. So therefore V2 stays at ground, and this ground can be called as virtual ground. As long as op-amp is ideal, the voltage at V1 will be equal to voltage at V2. So right now the V1 terminal is connected to physical ground, so V2 will be at virtual ground. So this is very important for analysis of circuits, the virtual ground concept especially. Okay. So difference voltage applied between the non-inverting and inverting terminal, that's labeled as VID. Okay. That's VID. This is difference voltage. Now, so op-amp is used in inverting mode. We can see here the resistance, feedback resistor RF. And here you can see that we have taken 4-bit binary data as input, B0, B1, B2, B3. These are all switches, so that simulates our digital input. So this is basically digital to analog converter. Therefore input will be the digital. When we say digital, then question rises here, how many bit digital data we are applying. So in this example we have taken 4-bit digital data, namely LSB is least significant bit is B0 and the most significant bit is B3. So B0, B1, B2, B3 represents 4-bit digital data in our example. Okay. So when we say digital data, the lower level is 0 volts and higher level is going to be 5 volts. Okay. Logic 1 is 5 volts and logic 0 is 0 volts. Okay, that's the digital data we apply here. Sometimes the digital data can also be simulated or applied through a counter called as 7493. This counter you might have studied in digital electronics. The same counter can be used here to apply different sets of the possible combination of digital data. Therefore this block here that I have shown that can be replaced with a 4-bit counter, namely 7493, to simulate the binary inputs here. Okay. Now when it comes to resistor here, you can see the smartly we have chosen here the resistors. The first resistor, the resistor in the first branch here we have taken as R. Let's assume R as 10 kilo ohm. This is a 10 kilo ohm. And the second resistor we have used here as R by 2, R by 4, R by 8. This is in the form of some weight in the form of binary weights. The resistors used here resembles binary weight. So it's in the form of 2, 4, 8 divisible by 2, 4, 8. So that's very important in this circuit here. So if I assume R as 10 kilo ohm, naturally the R by 2 will be 5 kilo ohm, R by 4 is 2.5 kilo ohm, R by 8 is 1.25 kilo ohm. The current flowing through these resistors is labeled as I1, that is the through first branch. Similarly, current flowing through I2 when the switch B1 is closed is labeled as I2. When the switch is open, current will not flow, therefore I2 will be 0. Same as here, when the switch B0 is closed, current flows through I1 from the supply to the through the op-amp. So I1 is the current flowing through the branch 1. I2 is the current flows because when the switch B1 is closed. I3 is again current flowing through the third branch when the B2 switch is closed. When it is open, I3 will be 0. Similarly, I4 represents current flowing through the fourth branch when the switch B3 is closed. That's connected to the plus 5 volt supply. Okay, so here now one more observation what we can make here is the op-amp here which is in inverting mode works as voltage to current converter. Okay, sorry, current to voltage converter. The current here coming I1, sum of all these currents depending on whichever the switches are closed, the total current coming here is converted into the voltage here. The load resistance is optional here. In case if it is required, we can use 10 kilo ohm as load resistor to measure the output voltage. So this is whole the complete circuit, which is 4-bit binary weighted resistor type digital to analog converter. The digital data, 4-bit data that we apply here gets converted into analog data and appears across V0. Okay, so this is the circuit description. Later on we will go and explain the working of this digital to analog converter. So before we move on to further working, let's see the points which I have covered with reference to this D2E converter. Now, as we have shown, the figure shows digital to analog converter, which is based on op-amp, and binary weighted resistors are used. Op-amp is connected in inverting mode. However, op-amp also can be connected in non-inverting mode also. Don't assume that op-amp always has to be in inverting mode. It can also be connected in non-inverting mode. Okay. So number of binary inputs that we have assumed here is 4 because it's a 4-bit binary weighted resistor type digital to analog converter. That's why this analog converter can be called as digital to analog converter can be called as 4-bit D2E converter. Following next point, since the number of inputs are 4, there can be totally 16 possible combinations. Namely, B0 is LSB, B3 is MSB, most significant bit. The possible combinations can vary from 0, 0, 0, 0 all the way up to 1, 1, 1, 1. Okay, there are totally 16 combinations here. That means the circuit that we have shown here can take all those possible combinations. But digital data here can be all zeros, that means all are open. It can go up to all the way up to all closed, that means all are 5 volts. So 16 possible combinations we can apply here, since it's a 4-bit digital to analog converter, and for each combination we can have a different output voltage. Okay, so with that we will proceed further. Let us take an example and see that what is the analog voltage for some combination of digital data as an input. We'll go through an example here. So if assume here B3, B2, B1, B0 as 0, 0, 0, 1. That means in the circuit we are closing switch B0. That means B0 is connected to plus 5 volts. Remaining switches B1, B2, B3 are connected to 0 volts. That means there is no current through these switches, but current flows through the switch B0 in the branch B0, where the branch, the first branch where B0 switch is placed, since it's connected to 5 volts. Now we already know about virtual ground concept. I don't want to repeat again here. V1 is physically grounded, so V2 will be in virtual ground. Now voltage across R is plus 5 volts, that's the first branch voltage is across that is 5 volts. So therefore current through the first branch resistor is given by voltage across the resistor divided by the resistor value. Let me go back to circuit and explain here how exactly we are taking. So we assume this B0 switch is closed. You can see in the circuit B0 is closed, remaining switches are in open condition. So therefore since it is B0 which is closed, it is tied, the resistor R is tied to 5 volts. Current flows through the resistor R, so I1 exists, whereas I2, I3, I4 are going to be 0. So what is the voltage across this 10 kilo ohm resistor? The voltage across this R or 10 kilo ohm resistor is 5 volts divided by 5 volts divided by this 10 kilo ohm resistor, that gives me the current I1. Okay, once we know I1, then we can calculate the output voltage here. Okay, so let's go through the example continuation. So I1 is 0.5 milliampere because voltage across R is 5 volts, the resistor value is 10 kilo ohm, so therefore I1 is going to be 0.5 milliampere. Since op-amp doesn't draw any current, that is IB current going into the op-amp is 0, the complete current coming from the resistor R through R goes to the feedback through the feedback resistor. So I1 will be equal to IF, since IB is approximately equal to 0, so IF will be now equal to 0.5 milliampere. Now to calculate output voltage, we have an expression. This expression is already familiar to you. Output voltage is equal to voltage at inverting terminal minus drop across the feedback resistor. Voltage at inverting terminal is 0 because of virtual ground, and we need to calculate drop across RF. Drop across RF is IF times RF, so therefore V0 is equal to minus 0.5 milliampere, that is feedback current, into RF is 1 kilo. We have assumed as RF as 1 kilo. Therefore output voltage is minus 0.5 volts. Okay, so this is the output voltage for the input combination 0, 0, 0, 1. So now we came to know that for this particular combination of input, the output voltage is minus 0.5 volts. Let's take another example where we change our input combination to 0, 0, 0, 0, 1, 0. Now B1 switch is connected to 5 volts since it's closed. Remaining switches B3, B2 and B0 are connected to 0 volts. There is no current through those resistors since they are connected to 0 volts. Now current through the second branch where we have tied to 5 volts is the resistor is R by 2. So current through R by 2 is let us call as I2, which is equal to voltage across R by 2 divided by the resistor value is R by 2. Voltage across R by 2 is plus 5 volts, so therefore the resistor value is 10k by 2, which gives me 1 milliampere current. Okay. Now since op-amp doesn't draw any current, now feedback current will be equal to the I2, so which is twice the I1. Previously we have seen I1, and here the I2 current will be double than that of the I1 current. So now with the help of output voltage equation, we can calculate output voltage. V0 is equal to minus IF times RF minus, now here I2 is 1 milliampere times 1 kilo ohm, which gives me minus 1 volt. We can observe here when the combination is 0, 0, 0, 1, output was minus 0.5 volts. Now for the combination of 0, 0, 1, 0, the output voltage is minus 1 volt. It has doubled. Okay. Now if you see the output voltage for the combination 0, 0, 1, 1, so previous two cases can be the current flowing through the previous two can be summed up. That's I1 in the first case 1 is 0.5 milliampere, I2 is 1 milliampere. Therefore for this particular combination, since B0 and B1 switches are closed, so IF will be the sum of these two. So I1 is 0.5 milliampere, I2 is 1 milliampere. Therefore total current flowing for this combination is 1.5 milliampere. Once we know total current, the output voltage can be calculated using the same equation. So V naught is equal to minus IF times RF minus 1.5 milliampere and 1 kilo ohm. So therefore output voltage is minus 1.5 volts. So this is the output voltage for the input combination as 001. Okay, so depending on B0, B1, B2, B3 switches open or close, the binary weighted currents are set up in the input resistors. Now I have shown for three examples, three cases for the input data what is the analog voltage. Similar procedure can be carried out for remaining combination also. So one can calculate for all 16 combinations what is the analog voltage. Okay, that's a procedure we can apply. Some of these binary weighted resistors are equal to the current flowing through the RF because op-amp doesn't draw any current. The proportional output voltage is calculated based on the binary weighted currents. That's already we explained. When all switches are closed, we can derive mathematical equation for output voltage. Here we are not going to derive since we are we are writing the output voltage equation as when all switches are closed as follows. So V naught is equal to minus RF because minus is because op-amp is used in inverting mode. B naught divided by R, that's the switch connected to resistor R. B1 divided by R by 2, B2 divided by R by 4, B3 divided by R by 8, where B0, B1, B2, B3 represent switches which can be open, that means it is 0 volts. When it is closed, it's plus 5 volts. Now, so this equation is very important for any combination of B0, B1, B2, B3. We can calculate output voltage. Output voltage is also proportional to the feedback resistor. If you change the feedback resistor, then output voltage, corresponding output voltage changes. Now, the digital to analog conversion, binary weighted resistor type digital to analog conversion can be shown on a graph where we plot the conversion on the graph. The input binary inputs or digital input is taken along the x-axis, plotted along x-axis. Analog output is shown along the y-axis. As we know that we have assumed a 4-bit digital to analog converter, there can be 16 possible combinations. So instead of representing in binary, we have represented in decimal equivalent of binary. So this 0 represents B0, B1, B2, B3 as 0, 0, 0, 0. Okay, and 15 represents all ones. Okay, so the digital input is shown along the x-axis, and the analog outputs are shown along the y-axis. Analog output varies from minus 0.5. We have seen already for the input combination 0, 0, 0, 1. For the combination 0, 0, 1, 0, we have seen analog output voltage is minus 1 volt. For 0, 0, 1, 1, we have seen analog voltage is minus 1.5 volts. Similarly, if you continue like that, the analog voltage for all binary ones is going to be minus 7.5 volts. So analog voltage versus digital input is basically a staircase waveform. This is in the form of a staircase where total number of steps would be 15, ignoring this 0 the step. The step size here is going to be minus 0.5 volts. You can see here from one step to next step, the increment is minus 0.5 volts. This step size can be varied by varying the feedback resistor value. Okay, so this is a negative going staircase waveform. This graph represents a plot between digital input and analog output. Okay, so maximum output voltage also one should note here the maximum voltage in this circuit should not exceed plus VCC and minus VE, almost equal to plus or minus VSAT. So one should ensure while designing digital to analog converter, the output voltage of op-amp should not exceed plus or minus VSAT. In our example, 4-bit digital to analog converter, you can see here the maximum voltage when all combination is 1111, so it's minus 7.5 volts. Okay, so this once has to be ensured, which is less than the plus VCC and minus VB. Okay, so now let's see few disadvantages of this binary weighted resistor type DTA converter. So the main drawback of this binary weighted resistor type DTA converter is the resistor itself. It requires binary weighted resistors. We have seen that binary weighted resistors are R by 2, R by A, the 8 we have R by 4, R by 8 we have used. So the choosing those resistor values is very difficult. Here we have used 4-bit digital to analog converter. So the circuit seems to be simple, but for more number of inputs, for example, when the digital input data is more than the 4-bit, then more resistor combinations are required. To obtain the more resistor combinations, it's not practically feasible. So therefore, this is the main drawback of binary weighted type digital to analog converter. This drawback can be easily overcome by using only 2 sets of resistors instead of using R by 2, R by 4 and R by 8. In the next circuit that we are going to discuss, we use only 2 type of resistors. One is R, other one is 2R. This overcomes the drawback of binary weighted type, weighted resistor type digital to analog conversion. Okay. Now we'll proceed with the next D2A converter, which is R and 2R resistors type digital to analog conversion. This is the circuit diagram for R and 2R resistor type digital to analog conversion. We can see here the switches are shown here as same notations we've used here also. B0, B1, B2, B3 are the switches that are used to simulate or apply the digital data. This can be simulated even through the counter 7493 that we have shown in the previous circuit. Op-amp is used in the inverting mode, where we apply input signal to the inverting terminal. Non-inverting terminal is grounded here through this supply. Implicit power supply of op-amp is plus VCC equals plus 15, minus VCC is minus 15. Since non-inverting terminal is physically grounded, the inverting terminal will be at virtual ground. Okay, so here we use feedback resistor value as 20 kilo ohm, and there is an optional load resistor value. When we want to measure output voltage, we can use load resistor value as 10 kilo ohm. And we can observe here the resistor combinations. Here we have R2R, R2R. Only 2 type of resistors we have used here. That's why this circuit is more efficient than the binary weighted resistor type digital to analog conversion. So here we assume 2R values as 20 kilo ohm, therefore naturally R value will be 10 kilo ohm. Okay, so this is the input data, digital data can be applied. B0 can be closed. When it is closed, it's connected to 5 volt. So when it is open, it's connected to 0 volts. So all the switches can be connected to 5 volts or 0 volts. So whenever we connect it to 5 volts, current will flow through that corresponding branch, and the total current can be calculated. From this total current, the feedback current will be calculated. From the feedback current, output voltage can be determined. Okay, so this is how the circuit works. Okay, so now let us go through the description of this circuit. The figure shows the circuit diagram of D2A converter based on only 2 type of resistors, R and 2R. B3, B2, B1, B0 represents switches. These switches will simulate the binary input. The output voltage is proportional to the binary inputs. As you keep increasing the binary combinations, so output voltage also increases. So B3, B2, B1, B0 can be 0 volts or it can be 5 volts. Let's take some examples so that we will understand how this R to 2R resistor based digital to analog converter works. Let's assume the input combination B3, B2, B1, B0 equals 1, 0, 0, 0. We have made here MSB as 1, and we'll see that how we'll see that what value the analog value represents for this digital data. Okay, so here for this particular digital data, B3 is connected to 5 volts, B2, B1, B2 are connected to 0 volts. We can draw the equivalent circuit, we can simplify the previous circuit shown to this when only B3 is acting. So B3 is closed. So the equivalent circuit is as shown here. So all the resistor values we can calculate the Thevenin's equivalent of all the resistors, so it becomes equal to 2R. The calculations are shown below. So the Thevenin resistance is equal to 2R. Okay. So how we will calculate? We will show that. So current flowing through the, in this case I2 is going to be 0. The current flowing through I1 can be calculated by dividing the voltage by this resistor value. So I can be calculated, I will be equal to IF, then finally we can calculate the output voltage. So this is the equivalent circuit when B3 is 5 volts and B2, B1, B0 are 0 volt. So since there is no current flowing through the this resistance, so I2 will be equal to 0 ohms. Whereas I1, there is a voltage across 2R resistor which is 5 volts divided by 2R. So 2R value is going to be 20 kilo ohm. So I1 is found to be 0.25 milliampere. As I was mentioning that the equivalent resistor values can be called as Thevenin's resistance. The value can be calculated as follows. I will go back to circuit and explain how this Thevenin resistance can be calculated. So you can see here this 2R resistance is in parallel with 2R, so parallel combination of this can be calculated, that is in series with R, that's again in parallel with 2R, that is again in series with R. So this whole combination, the highlighted combination will be now again this is again one more branch is there is a parallel combination with 2R, and again that is in series with R. So this total combination will be equal to 2R, that anybody can calculate that, and that's what we have shown here. The R Thevenin is equal to 2R, which is equal to 20 kilo ohm. Since V2 is at virtual ground, the value is the voltage is going to be 0 at that point, at that node. I2 is 0 milliampere, I1 is now which is 0.25 milliampere, which is equal to IF and equal to total current coming from various branches. So output voltage now equals V0 is equal to minus IF times RF. IF can be substituted here. RF value is going to be 20 kilo ohm, that's assumed. So output voltage now is equal to minus 5 volts. Okay, so this is the output voltage for the input combination 1 0 0 0. So for this particular combination, output voltage is found to be 5 volts. Similarly, the same procedure can be used to calculate the output voltage for all possible input combinations. Since it's a 4-bit digital to analog converter, there can be 16 possible combinations. Let's take one more example to calculate the analog voltage. For the input combination B3, B2, B1, B0, we have assumed here as all ones. So this output here at this point can be called as maximum output voltage, or it can also be called as full scale output. Full scale output is nothing but it's the output voltage for the input combination as 1 1 1 1. Okay, so this full scale output voltage can be calculated using the following equation. V0 is equal to minus RF into B3 divided by 2R, B2 divided by 4R, B1 divided by 8R, B0 divided by 16R. Okay, so this is the equation we can use to calculate the output voltage. We can observe here in the denominator the resistors are in the multiples of 2R, so it can be easily chosen compared to the binary weighted resistor type digital to analog converter. As we already mentioned, B3, B2, B1, B0 can have the value 0 volts and 5 volts. Now for B3, B2, B1, B0 as 1 1 1 1, so the above equation can be used to calculate the output voltage. Let's see that now. So 1111 represents it's 5 volts. So therefore B3 is 5 volts, B2 is 5, and for all B3, B2, B1, B0 we can substitute as 5 volts, and 2R is equal to 20 kilo ohm. Therefore 4R becomes 40 kilo ohm, 8R becomes 80 kilo ohm. So 16R becomes 160 kilo ohm. RF we have assumed as 20 kilo ohm. Since op amp is in inverting mode, there will be a negative sign always. So V naught out voltage, the equation can be, the values can be simplified here. So on simplification, we can get the value output voltage as minus 9.375 volts. So this is called as full scale output or maximum output voltage. When the input combination is 1, 1, 1, 1 or 5 volts, 5 volts, 5 volts, 5 volts, the output voltage is going to be minus 9.375 volts. So this is well within the maximum output voltage, which is plus or minus VSAT. Therefore, this design is going to be accepted. Okay. So now we will show the table where in which for all the combinations of binary data. So we are showing here the analog output voltage. The same equation just now we have used can be used here once again to calculate the analog output voltage. So this table gives you the analog voltage for the different digital input combinations. For instance, 0, 0, 0, 5 volts, the analog output voltage is minus 0.625 volts. Likewise, we can also calculate for 3 decimal value as 3, binary value 0055, the analog voltage is going to be minus 1.875 volts. Likewise, you can calculate for all the combinations. Just now we have calculated full scale output voltage for when all the binary values are 1, so it's going to be minus 9.375 volts. This conversion can be represented on a graph. This graph already we have seen where we plot binary input or input data along x-axis, output data, analog output voltage along y-axis. The graph between digital input and analog output is going to be a staircase waveform. Okay, so we'll have here 16 combinations and corresponding 16 analog values are shown here. So the graph resembles here a staircase. Okay, the staircase, the step size, and the number of inputs, everything can be decided, it can be varied. Okay. Coming to the advantages, since it uses only 2 sets of resistors, this is more efficient compared to binary weighted resistor type digital to analog converter. Second thing is the disadvantages. When we look at disadvantages here, since this type of converter uses more resistances, R&2R combination resistances, it becomes more difficult to analyze the circuit when we go for higher digital inputs here than the binary weighted resistor type here. So for more than 4 digital inputs here, circuit also becomes complex and accuracy keeps decreasing for more more digital inputs here. Okay, so those are the drawbacks of digital to analog converters here. So with this, we have come to an end of explaining how to convert digital data to analog data. Digital data is basically a binary data. How to obtain its analog value, we have seen this through the 2 types of converter. The first one is binary weighted resistor type DTV converter. Second one is R-2R resistor type digital to analog converter. Okay. Next we'll proceed to the analog to digital converters. Analog to digital converters basically converts analog input to digital output here. As we already seen in the DTV converters, the analog value can be 0 to 5 volts. It can take any value in terms of voltage. The digital output is basically in terms of zeros and ones. The definition of analog to digital converter is A to D converter converts analog voltage to digital output here. There are variety of the analog to digital converters in the literature. A couple of them we have mentioned here. Single ramp type, single ramp integrating type analog to digital converter, dual ramp type analog to digital converter, single counter based, tracking based, and finally the very important and that we are going to discuss in today's class is successive approximation type A to D converter. Okay, so these are the totally 5 type of A to D converters can be seen in the literature. However, in our syllabus we have only the successive approximation type A to D converter. Let's try to understand how this successive approximation type A to D converter works. Successive approximation type A to D converter, will show the circuit diagram of successive approximation type A to D converter. In the circuit diagram, the heart of the circuit is 8-bit successive approximation register. This is very important a block, successive approximation type register. The output of SAR is successive approximation register is connected to the 8-bit digital to analog converter. ADC implies digital to analog converter. So the precision or accuracy of analog to digital converter depends on the precision of digital to analog converter. Okay, since it employs digital to analog converter. The output of digital to analog converter is compared with the analog input using a comparator circuit, and based on the value, the output value of comparator is fed to the successive approximation register. The block diagram of successive approximation register type A to D converter is as here shown here. I'll try to minimize this so that you can see whole circuit. Still, I think, yeah. Now we can see complete circuit here. This is the block diagram of successive approximation type analog to digital conversion. So here we have an 8-bit successive approximation register. The second block is going to be the DAC. Since we have 8-bit SAR, successive approximation register, we are supposed to use 8-bit digital to analog converter. So we give here digital data from B0 to B7. This digital data is converted to analog value. The output of 8-bit DAC is labeled as VA. This analog voltage is compared with the analog voltage that requires conversion, and based on this which one is larger, accordingly the output of comparator will be the plus VSAT or minus VSAT. So the serial data coming here will be registered here. The serial data may be 1 or 0, that is registered in the 8-bit SAR, and so the data again coming out from this is given back to the DAC. So this is basically a cycle here, loop here. So the heart of the circuit is the 8-bit SAR. This block is the heart of the circuit. This works on the clock cycle. Each time when the clock is rising edge is applied, the clock keeps the changing this data. And apart from this, we have other signals like serial data output. The complete data converted bit by bit digital data is going to be output here. And we have a signal to initiate the conversion process. We have a start signal, and once conversion is completed, we have a conversion complete signal which is going to become 1. The converted digital values appears here. So we extract the data from the 8-bit output of 8-bit SAR. Depending on the signal here, if it is high, then only this latch registers the values of Q0, Q1, Q2, Q3 up to Q7. That data, once it is latched, that it appears at the output of a latches. So this is the digital data output. So we apply input here, and this go through the cyclic process, and finally once the conversion is over after so since we are using here 8-bit SAR, at least it requires 8 clock cycles. So once 8 clock cycles is completed, so your digital data is ready to read here.
Okay, so this is the way it converts. The working of this can be further understood by going through the example. So 8-bit latches here, that is, as I already told you, this is an 8-bit latch which holds 8-bit digital data at the end of the conversion. Okay. Now let us understand the working process. First, one has to apply the start signal. Once start signal is applied, this initiation, this 8-bit SR will work based on the clock. So assume that in the first clock raising edge start signal is applied. In the following raising edge, the SCR will set Q7 as 1 and remaining bits Q6, Q5, Q4, Q3, Q2, Q1, Q0 are set to 0. Only Q7 is set to 1, remaining bits are set, the SCR will set as 0. So this data is given to 8-bit digital to analog conversion. So for since Q7 is set to 1 here, B7 becomes 1, remaining binary combination is going to be 0. For this input combination, 8-bit digital to analog converter converts into the analog voltage. This analog voltage is compared with the input voltage. Suppose if analog voltage is less compared to the analog input, if VA is less compared to Vin, output will be in minus Vsat. For other option, when VA is going to be, when VA is less compared to Vin, output will be at plus Vsat. When VA is more compared to Vin, output will be in minus Vsat. Okay, so the comparator output will set or reset the data going to the 8-bit SCR. Okay, so this since in the first cycle we have tested by making Q7 as 1, in the next cycle we have to make Q6 as 1, remaining bits as 0. Okay, so in this way the all bits has to be checked, and finally when the LSB bit is made 1, remaining bits are going to be made as 0. The corresponding end of CC will become activate and the output will be latched. So detailed working of this can be understood here. As I told you already, we need to apply start of conversion signal. Yes, that should be made high. So SAR will reset. If in previously if SAR has been set, now it will get reset. It will start with freshly with all values as 0. In the first clock cycle, for the rising edge, Q7 of SAR is set to 1. Now, digital to analog converter, the second block generates analog voltage as VA. For the Q7 bit has made 1. Now, VA is compared with the analog input voltage. VA is nothing but the DAC output. Vin is the analog input. These two voltages are compared, and accordingly decisions are made. If VA is greater than Vin, comparator output is going to be at minus Vsat. That's logically it's equal to 0. So VA is nothing but DAC output. Now, once this condition is satisfied, successive approximation register clears Q7. It will make Q7 as 0. Otherwise, if analog DAC output is less than the analog input voltage VA, now comparator output is at plus Vsat, because the VA is less compared to Vin. Logically it's equivalent to 1. Now corresponding to this, now SCR will set Q7th bit or MSB bit. Okay, so whether Q7 bit has to be set or reset depends on this condition. For VA greater than Vin, Q7 will be reset. For VA less than Vin, Q7 will be set. So in the next class cycle, SR will set Q6. Already we have tested Q7. Next it will proceed with Q6. Now depending on the output of a comparator, SCR either it has to keep or reset bit Q6. So this process will be continued since until SAR tries for all the bits starting from Q7 to Q0. As soon as LSB Q0 is tried, SAR forces, successive approximation register forces conversion complete signal. It will make CC as high, and once CC signal enables, the same CC signal enables a latch, and once latch is enabled, digital data appears at the output of a latch. So digital data is available serially also, as we have shown serial output signal of a from an SAR. So that also determines bit by bit digital output. CC can be connected to start of conversion signal, which we have seen in the circuit. Once we connect CC to the start of conversion, the converter will continuously converts analog data to digital data. 8-bit successive approximation type 8-way converter requires at least 8 clock cycles to convert complete analog to digital conversion. So this is about successive approximation type digital analog to digital conversion. So with this we have come to an end, and so in a nutshell, to summarize, we have discussed in today's class 2 types of digital to analog converter, namely binary weighted resistor type digital to analog converter, R-2R resistor type digital to analog converter, and we have discussed one circuit diagram to convert with that converts analog data to analog input to digital output, namely the successive approximation type analog to digital conversion. So thank you all for listening. I hope you understood the topics that I have covered in today's class. Thank you one and all.